All right, in the first section of notes of Unit 7, we're going to look at some introductory information about electrons. So overview here, chemistry is really all about electrons. And if you recall, they're subatomic particles like protons and neutrons, but they don't really behave like particles. In fact, this is why we have this Bohr model, Bohr, that is a scientist named Niels Bohr. And if you recall, this is kind of a still popular representation of an atom. This is like called the planetary model. You have the electrons moving in these orbits around the nucleus. We call this the orbital model. So electrons actually really behave more like waves. And a lot of the study of light experiments have given us information about electrons. So that's not really true, although it's like classically kind of still used. This is actually more accurate because electrons don't zoom around like in fixed orbits, but rather they're found in an electron cloud, and that's based on probability. But we'll get into that at a later time here. All right, so overview, reminder that the atom is held together by forces. So mainly the electromagnetic force and the strong nuclear force. And there is attraction between electrons and the nucleus, but what's preventing these electrons from being pulled into the nucleus? Well, first of all, electrons have a lot of energy. They have an insane amount of energy here. Can't move myself. There we go. All right. The energy keeps them in constant motion around the nucleus. And the energy of an electron can change with radiant or light energy. And this is called electromagnetic radiation. So this is what we'll focus on in this lesson, is looking at some electromagnetic radiation. And then also our second practice, you'll be looking or using the equations in here. So first of all, what is EMR, or electromagnetic radiation? We have a spectrum here that has different colors, different frequency and wavelengths of light. As we are down on the left-hand side of this scale, we have longer, lower frequency waves like radio waves, microwaves, infrared. Visible light is just a little tiny section of the electromagnetic radiation spectrum. And then you have UV, X-ray, and gamma ray. These are high energy, high frequency, and very short wavelength kind of radiation. So the definition of electromagnetic radiation is a form of energy that exhibits wave-like behavior as it travels through space. And these are all examples. So here is this tiny little piece in the visible spectrum, Roy G. Biv. And red, by the way, depends on how the spectrum is set up, but in this case, red is longer. Well, I mean, red is on the left-hand side, which makes it longer waves, lower energy. Purple, if you think of violet UV is right next to it. That's a very high energy, high frequency, short wavelength. So the EMR, or electromagnetic spectrum, is all of the different forms of radiant energy. So whether we can see it or not, it exists, and this is encompassing all of that. Radiant energy travels as waves through empty space at the speed of light. This is a constant, 3 times 10 to the 8th meters per second, and this is for every single particle. This is a constant for any kind of light energy. We can also quantify waves by looking at their wavelength, which is represented by lambda, kind of looks like an upside down Y. Frequency, which is represented by nu, Nu, that's just a Greek letter, kind of looks like a V. And then energy, usually they use capital E for that. So important to understand the relationships. Again, down here on the left, we have radio waves, which are longer wavelength, lower frequency, and lower energy. So longer wavelength, lower frequency and energy. On the other side is going to be the opposite. So shorter wavelength gives us high frequency and high energy. I just always think of like really fast versus like really slow. And that would give it less energy if it's slower. Okay, the velocity of a wave can be calculated as velocity equals lambda nu, which, remember, speed of light is 3 times 10 to the 8th meters per second. So that can be written for electromagnetic radiation. This is a formula that you should write down. You do not have to memorize it. However, we should know like C is standing for speed of light, and then this is wavelength, and this is frequency. So if you know those, you don't have to memorize like the formulas. We just need to know like what the variables stand for. Wavelength, again, is upside down y, which is lambda. This is a unit of distance for measuring waves. We often use nanometers, but when we plug it in, we have to have it in meters, and that's so that the units will cancel with that meters per second. Frequency, which is represented by nu, the fancy V. This is the number of waves that pass a given point in a certain time. And we use hertz, Hz, as your units. That's also the equivalent to waves per second or inverse seconds. Sometimes we use that as well, like 1 over s or s to the negative 1. That's the same thing as well. And again, these in the practice, the first practice is just conceptual and using the electromagnetic spectrum to interpret relationships mostly. And then the second one, I do have a separate video on examples of how to solve these problems. They are just algebra. You just are given everything but one variable and you just plug it in. The hardest part is the units, just making sure that you're keeping track of what units you're talking about. All right, here's the electromagnetic spectrum again, in just a different way. Again, the colors and some different frequency or different radiation are lined up with your wavelength and frequency. You can pause this and take a look at that. So the relationship between wavelength, frequency, and energy. Wavelength and frequency has an inverse relationship. So as one goes up, the other goes down. As wavelength increases, frequency decreases. And then frequency and energy have a direct relationship. So the greater the frequency, the greater the energy, or vice versa. So as frequency increases, so does energy. All right, electrons and the EMS. So how does this have to do with anything? Well, first of all, this is quite complicated, and so we're making it as simple as possible, but we have something called the photoelectric effect. This was an experiment that was done by some physicists, and basically what they did is they shined light down on metal, and if they were able to hit a certain threshold, electrons were emitted. So when electromagnetic radiation strikes a metal and electrons are emitted, this is called a photoelectric effect. So the light must be a certain frequency in order for this to occur. This led to the concept of what's called quantum. And a quantum, and plural is quanta, is the minimum amount of energy that can be gained or lost by an atom. So we have a second equation, and you'll notice nu is in here as well. So that's the overlap, is that frequencies in both of these equations. I like to sometimes call this the particle equation and the other one the wave equation. So the particle equation, because electrons can move like waves, but they also can move like particles. It's very much quantum physics. So we just accept that's how we know a lot of information about electrons in chemistry. But we could also calculate, which we will do in a lab. So this formula I would make sure you have this written down. This is energy equals, this is called Planck's constant. And again, it's just a constant. If you'd like to know how it was derived, feel free to look it up. It's quite complex. And then times frequency. So energy in a quantum of electromagnetic radiation is E, and this is measured in joules. So joules is actually the SI unit for energy. And then H is Planck's constant, and it's a kind of a weird number, very, very small, and it has a weird unit. It's joules times seconds. And again, once you plug it in, you can see like everything should cancel but the unit that you're solving for. So this will be in our second practice. And again, I'll have a short video that you can use as needed to, have some models on how to solve these problems. And then nu, or the V, is frequency, which is measured in hertz or inverse seconds, 1 over S. So electrons exist in specific energy levels. The ground state is the lowest state. You can see the picture here. A ground state electrons can change and they can move to another state. If they absorb energy, they'll jump to a higher energy level. It's called the excited state. And they can have many excited states. They only have one ground state, though. Ground state's the very bottom, and then your excited states are higher energy levels. Now, when they drop back down, this is going to, electrons, this is very unstable and very temporary as far as electrons are going to move to an excited state, but they're going to drop back down eventually. And when they do this, they're going to release energy in the form of light. The emission spectrum is the spectrum of light released from excited atoms of an element, and we'll take a look at that in an activity. This is actually going to determine the color of light given off. I think that's it.